So what we're going to look at in the next chapter has to do with what's called a chi-square goodness of fit test. So there's a couple different types of chi-square tests that we're going to look at. The first of which is this up top here, which is what's called a chi-square goodness of fit test. And a chi-square goodness of fit test essentially is when you have a one-way table and you're looking to see collectively, if in your one-way table, if any of the values that are in your table seem to be different than statistically significant, and have a difference that would be different than what you would expect. There's also a couple other different chi-square tests that we'll look at later. One is what's called a chi-square test for homogeneity. The other is a chi-square test for what's known as association and independence. So we'll take a look at those two types of tests later. But what we're really going to focus on here at the beginning of this is what's called a chi-square goodness of fit test, which is typically used when you have a one-way table. So here's an example of a one-way table. So we have for a bag of M&Ms, the one-way table display the distribution of the categorical variable for the individuals in the sample. So what we have is the color of the M&Ms, blue, orange, green, yellow, red, and brown. Total of 60 M&Ms, and how many for a given bag of M&Ms, what the color distribution was for a randomly chosen bag. So if you notice here, just talking, the sample proportion of blue M&Ms in the bag would be 0.15. So this is what we're observing from the randomly chosen bag that we have here. However, the company claims, the Mars company that makes M&Ms, they claim that 24% of their candies are blue. So if you take a look at the difference in the proportions there, so you have 24% is what you would expect. However, when we randomly chose a bag, we only got 15%. So one of the things that we do with questions like this is we perform a significance test, and here would be sort of the null and alternative hypothesis if we were just talking about comparing the blue candies that we actually got versus what the Mars company claims is true. So when we're going through a chi-square goodness of fit test, one of the things that we do is we basically take the one-way table and we take all of these values that we have here and we look at them collectively to see if there's anything in all of the colors together that would suggest that the company's claim is not true. So one of the ways you could go about this is we could do 6 different significance tests for each of the 6 different colors, and that's kind of what I'm referring to down here at the bottom. Is that's a very inefficient way of doing that. So what we do is we do a chi-square goodness of fit test where we kind of lump all the colors together. So just looking at null and alternative hypothesis. So the null hypothesis for a goodness of fit test for this, we would say, is that the company's stated color distribution for their candies is correct, whereas we could say the alternative would be is that their color distribution is not correct. So that's one way of sort of stating the null and alternative hypothesis for this. Another way would be to actually list what all of the proportions are for each of the colors. So this is what the Mars company claims is true for the color distribution of their M&M. So they claim that 24% of the candies are blue, 20% are orange, 16% are green, 14% are yellow, 13% are red, and then another 13% are brown. So the alternative for this would just be that at least one of those colors would be incorrect. So the idea of the chi-square test is what we're going to try to do is we're going to compare what we observed from our random sample, and the random sample would be the contents of a bag of M&Ms versus what we would expect to happen based on these percentages that are given up here. And are any of those values collectively, are these values drastically different than what we would expect? So if you think about the random sample of 60 candies in the bag, if we're talking about 20, or we would expect 24% of them to be blue, then we would expect somewhere around 14.4 of those candies to be blue. Now in this case that didn't happen. So what we're looking at in terms of all of the different expected counts, if we go through each one of these, so orange, since 20% of the candies were orange, there were 60 total candies in the bag. These would be all what we call the expected counts. And we're simply just basically taking the percentage that the Mars Company gives us, and we multiply each of those by 60 because that's how many M&Ms were in the bag that we chose. So these are all what are called the expected counts. So you got the 14.4 up here for blue, and then the rest down here for the other orange, green, yellow, red, and brown colors. So just kind of doing a side-by-side comparison of what we observed that was in the bag of 60 M&Ms versus what we would expect to get in the bag of 60 based on the percentages that are given there. And what we're basically looking at is comparing each of the colors individually, but we're also trying to measure the differences collectively. So if we're talking about computing what's called a chi-square statistic, this is the formula that you use to do that. Now there is a way to compute this value on your calculator, and we will talk about how to do that, but essentially what you're doing for each one of the colors is you're taking the observed minus the expected squared, and you're dividing that by the expected. So you're doing that for each color, and then this right here, this is the sigma notation for the sum of all those values together. So just a question here, and it says the Mars Company states that the color distributions are 23% for blue and orange, 15% for green and yellow, and 12% for red and brown. Joey bought a bag of peanut chocolate candies and counted the colors of the candies in his sample. He got 12 blue, 7 orange, 13 green, 4 yellow, 8 red, and 2 brown. So just note at the top here that this is a little bit different than a regular bag of M&Ms. This is what the color distribution is for a peanut bag of M&Ms. So question number 1 says to state appropriate hypothesis for testing the claim of their percentages. So one way to list this would be to just simply list what the percentages are for each of the colors. That would be the null hypothesis. And then the alternative would be is just to say at least one of those percentages is not true. Question 2 says calculate the expected count for each color, assume that the company's claim is true. So if we're talking about the expected counts, we're basically looking at, for blue and orange, 23% of 46 candies that were in the bag. That would be 10.58. For green and yellow, those were 15%. So if we took 15% of 46, that's 6.9. And then 12% of 46 would be 5.52. And then it says for number 3, to calculate the chi-square statistic for Joey's sample. So what we're going to do with this is we're going to take for each color, we're going to take observed minus expected squared divided by expected, and we're going to do that for each of the colors. So right here is blue, and then we have orange, and then there's green, and then yellow, and then red, and then brown at the end, and this is what the collective score of that would be, 11.3724. So this 11.3724, that is what's referred to as the chi-square statistic, at least for this particular problem anyway. So if we come back to just the regular bag of M&Ms, not the peanuts, but just the regular bag of M&Ms, and we're kind of looking at, once again, talking about the chi-square statistic. So this was the original bag of 60 M&Ms. This is what we observed. And then based on the percentages that the Mars Company gives you for the regular bag of M&Ms, this is what we would expect to get out of the 60 that were in the bag. And here's the chi-square statistic for each one of those. And then here's the value for that. So we would say 10.180. So one of the things, just kind of sort of interject here, and I think this is probably an appropriate time to do that, is that when we're talking about the chi-square statistic, one of the things that we're looking at as far as the null and alternative hypothesis, the further this value gets from 0, the more likely we are to reject the null hypothesis. And there's other factors that are at play here. As in addition to the chi-square statistic, there's also the number of categories that you have, and then obviously how much differences there are between the observed and the expected counts when you go to compute that statistic. So just at the bottom here, just sort of a point of note with the chi-square statistic. So when you have a measure of distance, which is essentially what the chi-square statistic measures, large values for the chi-square are stronger evidence against the null hypothesis because they say that the observed counts are far enough away from what we would expect if the null hypothesis were true. whereas smaller values for the chi-square statistic suggest that the data are consistent with the null hypothesis, which means it doesn't give us reason to suspect that the stated percentages are in fact not true. So some different things when we're talking about expected counts. So when you have, and this is sort of one of the conditions that we'll look at in the next lesson, but when expected counts are all at least 5, the sampling distribution of the chi-square statistic is close to what's called a chi-square distribution, with the number of degrees of freedom equal to the number of categories minus 1. So just a sort of a visual illustration of what that looks like. So you can see here that the original chi-square curve with degrees of freedom of 1 has a very strong skewed right type of effect to it. And then as the degrees of freedom increase, as the number of categories increase, you can see that this graph starts to look more symmetric the more categories that you have, meaning that as the degrees of freedom increases, the more roughly symmetric that this curve will start to look like. So that's what I was referring to when we talk about the value of the chi-square statistic and its different distance from 0 and the number of categories, and how that will affect the p-value for whether you're going to reject or fail to reject the null hypothesis. So we computed the chi-square statistic for the sample of 60 M&Ms to be 10.18. And because all the expected counts are at least 5, the chi-square statistic will follow a chi-square distribution where the number of degrees of freedom in this case would be categories minus 1, which is 5. And then here's just a screenshot of what the chi-square CDF is. So if we did the chi-square CDF from 10.18 to E99, and here's sort of the visual illustration of what that looks like from a graphical standpoint. So it's this area in here, okay, under the chi-square curve, which is what the p-value for this would be. So the p-value in this case ends up being a value that's somewhere between 0.1 and 0.05. So if we were doing, say, a 5% significance test here, we would end up failing to reject the null hypothesis, because although these counts have a distance that's pretty far away from 0, it's not far enough away for us at a 5% significance level to reject the null hypothesis. So just kind of showing you in your calculator where you can find the test statistic and the p-value for something like this. So if I could come over to here. So what you'll basically do is if you go to stat and you go to edit, and you put in L1 all of the observed values, so this is for the original M&N bag that we had of 60 M&Ms, and then you put the expected values in L2. So from here, what I'm going to do is I'm going to go to stat and I'm going to go to tests, and if you use your up arrow key, you'll notice letter D has a chi-square goodness of fit test. So I'm going to go to D, and when I do that, here's the screen that comes up. So we have observed values in L1, expected values in L2. The degrees of freedom, because there's 6 different colors in this case, 6 minus 1 would be 5, so we would have 5 degrees of freedom for this. And when I calculate this, it's going to give me a couple different things here, one of which at the top is the chi-square statistic. So I have something like that there, and then here's the p-value for this, and we'll get into looking at in the next lesson sort of some of the different things that are going to go with the p-value involving the 4-step process and things of that nature. So that's how you get the chi-square statistic and the p-value in your calculator. So this last question here, it says, let's continue our analysis of Joey's sample of the peanut M&M candies. And it says, confirm that the expected counts are large enough to use a chi-square distribution. So by large enough, we mean are all the expected counts at least 5 or more. So when we computed that from before, we noticed that all of the expected counts were at least 5. So we're okay to do that. So just keep in mind that with the peanut M&M question, there were also 6 different colors of peanut M&M. So we would say that that has 5 degrees of freedom when we do that. And then this says to sketch the graph that shows the p-value. So for something like this, the chi-square statistics for this ends up being 11.3724, and I'll show you how to get that on your calculator here in a moment. So this shaded area right here under the chi-square curve represents the p-value for this particular problem. And then question 3 says, use your calculator's chi-square CDF command. So I'm going to use, in this case, I'm going to use the chi-square goodness of fit test in my calculator. So if you go to stat and you go to edit, what I did here was I put the peanut data in L3 and L4 because I wanted to keep these in sort of L1 and L2 here. So if you go to stat and go back to tests and you go to the chi-square goodness of fit test, which in this case is letter D, and I'm going to put these in L3. That's where my observed value was, and my expected values were in L4. Once again, you have 5 degrees of freedom, and when I calculate this, here's the test statistic, 11.37. Here's the p-value, 0.0447. So in terms of the test statistic for this, that's going to give me that here. Like I said, we'll talk later about just some different things involving the p-value for this test. And because the p-value with this is so small, it says, what conclusion would you draw about the company's claimed color distribution? So based on the evidence that we collected from the random sample of the peanut bag of M&Ms, because the p-value was less than 0.05, in this case we would reject the null hypothesis and we would conclude that, and this is important that you see what the conclusion is here, that at least one of the proportions of M&Ms, peanut, chocolate candies of a particular color is different from what the company reported. So the rejecting of the null hypothesis doesn't tell us which of the colors seem to be the most different from what we would expect. It just basically says that based on the sum of all the differences, we seem to have evidence to suggest that the proportions that they're giving may not be true. So that's basically just sort of an introduction to what we're talking about with the chi-square goodness of fit test. What we'll kind of follow up with this is we'll follow up with just some different things involving the p-value. We'll also take a look at some different things with sort of doing a chi-square goodness of fit test in a 4-step process, state plan to conclude type of format in the next lesson.